Yes, sir,
So the
definitely.
topic I am going to cover is an adaptive protection technique for highly PV penetrated distribution system. So as of you know that our power system is changing, and we have been discussing from a long duration that renewable are coming in our power system. So presently we have observed that the renewables are introduced in our distribution system, and which makes our distribution system unidirectional power flow to bidirectional power flow. However, in the future, there is a chance that the inclusion of such type of a system will be also higher. And in some cases, like in European countries, perhaps the penetration level is more than 50 to 70%. So there was a discussion at every point of our power system that either our system needed some changes, or what type of modifications should be there in control technique to handle the power system stability. So I am targeting that protection issues with the renewable penetration in our system. So in this context, I am going to discuss that distribution grid and renewables. What are the microgrid protection system for distribution system? Relay issues with the penetration of renewable microgrid, adaptive setting, and different techniques we are having for protection of distribution system with renewables. So, as of you know that our conventional generators are a synchronous generator. They are far away from our load center. However, the power is carried from the grid, which is we are calling transmission lines, to the load center. So, in the earlier case, there was no sources in our distribution system. We only consume the power. So there we all are passive consumers, and unidirectional power flow is there. However, in our future grid, we'll be having several sources like PV, wind, and other type of diesel generators will be available in the distribution system also. So this will make the direction of a power flow whenever it is required. Means sometimes the power may also flow from the distribution system to the grid whenever it is required, or when the power is not required in the distribution side. So earlier, if you have observed, there is a direction of power flow is in one direction. Now the possibility is there that the direction of power flow will change. So that is called bidirectional power flow. So where we stand now, if you observe the renewable based DG, it is universally available power. Somewhere it is wind, somewhere it is solar. It is a substitute to fossil fuel, which is creating the pollution in our system. And if you observe the green energy revolution, then the possible option we are having that we have to go for a energy source which is green, means it does not affect the our environment. So world electric production through renewables has reached to 26.5% of total electricity at the 2017 end. Now again it is increasing. To align with the 2006 Paris climate, to reduce the temperature rise, we must have another source that is nothing but renewables we are telling. If you observe the renewable energy scenario in India, it is also continuously increasing, and by 2022, we are targeting a renewable energy that is of 175 gigawatt. This is the basic comparison of whatever the renewable power we are having. Traditional biomass is 13%, then biofuels 0.3%, then hydropower is 3%, then fossil fuel is the 79%. However, if you consider the solar we are having, that is nearly equal to 70 to 80 gigawatt we are having. So these are the geographical scenario of India, power in India. If you observe the capacity to produce the power from PV, that is quite high. However, we are having very less amount of power production from wind and other sources. So PV is nothing but a another alternate source where we can generate electrical energy. So this is nothing but the wind power. So according to area wise, the capacity to produce uh, wind power is comparatively less than the PV power. So, considering with the energy sources which will be included in our distribution system, now there is a possibility that either the distribution system will be operated with the grid connection or without grid connection. So, whenever we are considering without grid connection, then that is nothing but maybe considered as a microgrid. So, what is a microgrid? Microgrid is nothing but a group of interconnected loads and distributed energy resources within a clearly defined electrical boundaries that act as a single controllable entity with respect to the grid. It either can connected as a grid connected mode or islanded mode. So considering the autonomous grids we are having, which are mainly present in the remote or hilly regions, now we are having a prediction that this type of grid will be also available in our distribution system, where the penetration level will be more comparatively more than 50%. Considering the changes in our distribution system, the types of microgrid will be possible. They are AC microgrid, DC microgrid, or hybrid microgrid. So, what is the AC microgrid? Whenever we are talking about the PV source and the wind source, so basically they does not provide a constant voltage and constant frequency. However, we require a constant voltage and constant frequency to supply to the electrical loads. So for that region, what you have to do, we have to use the converters so that we can put a constant voltage and frequency to the grid. So for this region, using the converter, we have to convert the photovoltaic and wind sources, and we have to connect it to the system. So since all the bus we are having, they are connected to the AC system, and they can sustain without the power supply from the grid, it can be called as a AC microgrid. So the changes we are having here, that is, we're having the converters. So these converters are nothing but playing a big role in control and operation of the system. So now it becomes easy for control, but it adds some protection issues also in our system. So this helps in reducing the transmission losses as well as it reduces the carbon emission. Now, second thing, whenever we are having the conversion, like if you are having the uh, different type of AC to DC conversion, DC to AC conversion, then the conversion losses are increasing. And we have also, in case of AC, the reactive power and other things are also creating problem. That is the power quality issues will be there. So instead of that, thinking about the AC grid, then there is a possibility that we'll be thinking about the power in case of DC. Perhaps you have heard the first grid which is developed, that is nothing but a DC grid. So considering that the fight between the AC and the DC, there is a possibility that DC microgrid will be a solution in the future. So that will be a DC bus as you see in the slide. So we'll be having different type of renewable sources like solar, wind, micro turbine, fuel, battery energy storage system. So there will be power feeding to different type of DC to DC and AC to DC conversion. So in that case, we'll be having a low loss in our system, and it will be also economical. However, the problem in the previous type of thing is that we'll be having a issue with the protection system because the protection system is not designed for a higher voltage level or the standards are not defined because we are doing the business of protection from more than 50 years with the AC side. Now, if you are considering again to modify the system, then probably it is required that we will be modifying the system into two types. Either both AC and DC will be available. Wherever DC is available, we'll providing the DC to the load. and wherever AC will be available, will be supplying AC to the load. The combination of these two AC and DC buses may convert this distribution system into microgrid that is called hybrid microgrid. So this can be obtained with less conversion losses, and it's also economical. So mostly, if you observe that if you're considering the DC system, which is can be available from the PV, so this PV can be utilized at the lower end. However, if you're talking about the grid, they are having the higher voltage supply. The power can be coming from the grid with a higher voltage level like 33 kV or 11 kV. So in that way, it is possible that the lower end will be having DC supply. When the power is not supplied from the lower end like PV, then it can be having power from the higher end like 33 kV. So the power flow may be in that way, that is grid is supplying to the AC load, and the lower end will be having DC load. So in that way, what you have to do basically will be having DC breakers as well as AC breakers, and we have to coordinate this relay and the breaker, because if there is a fault in the DC side and the AC side relay is flipping, then that is the mal operation we make there. So this is also a possible option of a hybrid microgrid. So as we talking about this microgrid is a real thing, or they are nothing but a story. So if you are observing that different type of microgrid we are having, you can observe here that is a copper mine in Western Australia. We have found a microgrid that started in 2014 and commissioned in 2016. So it is having 7 number of 2 megawatt DC and 5 number of 1 megawatt DC sets. So and it is supplying very well, and it is producing the electrical energy. Similarly, we are having Africa, that one island is there, two large microgrids of wind diesel hybrid microgrid, 1.651 megawatt, and wind energy to 960 gigawatt, commissioned in 2019 to 2014. In case of Equator Guiana, you observe in the Africa, that is the mark, circle mark we are having in the Google map. So here we are having 5 megawatt solar microgrid. That is Princeton Power System provided an efficient energy management system in the microgrid system. So that is operational from 2012. In California, you observe that is the island. So we are having a microgrid. So we have 8 power inverters of 8 kilowatt each and 480 batteries of energy storage. Similarly, University of California in San Diego, USA, we have a university research and development project, 450 acres campus. So it is also built with the SCADA system for energy management. So considering the all over the world, in India also we have several microgrids existing. So where there exist. So basically, if you observe in Karnataka, Selco Solar Energy Company under Harish Hande and Neville Williams has developed a solar storage remote microgrid to provide energy access to Bekamti, Mangalore, Minder village, and each of these are DC microgrid. In Bihar, CM official residence at Rajbansi Nagar, Patna has 125 kilowatt solar setups. In Sundarban, Tata Power Solar has solar microgrid projects in Indrapur, that is 110 kilowatt. Tata Power in Rockland also has launched up TP renewable microgrid. So in March 2019, BSES Yamuna Power Limited commissioned the solar photovoltaic microgrid in partnership with Panasonic as a part of a pilot project to set up in East Delhi. In this figure, you see that Andaman Coast Guard microgrid is also available. So that is supplying a total 75 kilowatt PV, and it has also a battery bank. If you observe these advantages of this microgrid, then basically we'll be having reduced carbon emission and better reliability and reduced transmission loss. So these advantages may be utilized in our future in our distribution system. However, they also have disadvantages. So what are these disturbances may be possible? The possible disturbances are voltage and frequency deviation, protection issues. Now let us talk about the protection of the distribution system we are having. So in our distribution system, normally whenever fault occurs, the faulty section must be disconnected. To disconnect into the faulty system, we have a combination of overcurrent relay, fuses, and the recloser. So basically, if you are having the fault in the load side, the fuse should operate, but to replace the fuse, it is a problem. So in order to protect the fuse, the recloser may operate first. So if the recloser is operating and uh, the fault is not clear, then again whatever is trying to reclose, then fuse should operate. So basically, whenever we are trying to set the protection of a distribution system, the following things are used. That is, they have to be coordinated, like overcurrent relay, fuse, and a recloser. First, the recloser will operate. After that, fuse is operating. If still the fault exists, then overcurrent relay will take care. And basically, there will be IDFT type. As of you know that when the current increases, then time of operation should decrease. And within a particular domain of PSM, that is plug setting multiplier, they are coordinated with each other. So basically, what we are considering that normally we operate in the fuse saving mode, and consider coordination must be there in between the closure, fuse, and OCR. So what is by reliable relay? Reliable protection system should able to detect and remove the faulty section from the rest of the healthy system with proper selectivity. So to obtain this criteria, we should have following characteristic in our relay system. The first one is called dependability. So whenever fault comes to system, it should be detected. And if there is no fault, it should not be detected. So that is called a security. So this dependability and the security property of this relay, it should be there. If it is losing the dependability or security, then the proper or reliable protection system cannot be achieved. Apart from that, we also have the another characteristic that is called selectivity. So selectivity means if there is a fault in the line 3, then the relay R3 should operate, and the relay R3 should have a backup from this R2 and R1. So normally we observe that if the fault is there in the line 3, then fault must be cleared from the system and the line 3 should be disconnected. The load at bus 3 would be supplied still from the system that is called synchronous generator. So basically, what we are having the time of operation formula is nothing but like this. There is 0.14 for TSM divided by ASM into 0.02 minus 1. So if you are considering this relay R1, R2, and R3, then the characteristic will be like this. So if there is a fault in our system in line 3, this relay R3 should operate with a minimum time. If R3 is not able to detect, then with some backup, that is called coordination time interval, after some time delay, this relay R3 should operate, which is nothing but the blue line. If R2 is not operating, then after some time delay, this relay R1 should operate. It means that whenever we are providing the backup, this time delay is having an very good important role in our desirable protection system. So if you are talking about the protection issues with integration of renewable sources, the issues will be relay blinding, sympathetic tripping, islanding problems, loss of coordination, and auto reclosure problems. So let us discuss these problems in our system. So when you talk about this problem like relay blinding, what is a relay blinding in our system. Now, let us consider if there is raw renewable source in our system, the power is only coming from the grid, which is nothing but a synchronous generator. So when fault comes from in a system ahead of R2, this R2 and R1, they are coordinated. But if you include a renewable source like solar and wind at this system, so basically they have their own control technique. Due to that control technique, we try to maintain the voltage at this bus R2. So if the voltage is maintained, then what will happen? Normally, the current which is coming from the grid side, that will decrease. Now, earlier when the renewable is not connected, if the red line shown in this figure is the fault current, and because of that the relays are coordinated. Now, if renewable is included, the fault current line is blue line, which is not cutting the characteristic, then it may be possible the relay R1 should not be operated. It means what? The relay R1 is unable to see the fault. Means whenever it is required to provide the backup, this R1 will not operate, or R1 will be blinded. So that is nothing but called relay blinding. Now the second case we are having, that is called sympathetic tripping. So if you observe in the diagram, the fault is occurring in the upper line, which must be cleared from this relay R1. So if it is clear from relay R1, then we will say the selectivity is maintained. But during the fault we are having in the upper line, the renewable source which is connected in the lower line, it will also make the flow of fault current through this R2. So if this R2 is not having directional property or directional overcurrent relay, so what will happen? This R2 will also see the fault current, and this R2 will operate. So whatever the loads we are having, which we have connected in this lower bus, so it will be disconnected. So we'll lose the selectivity. So this is nothing but called sympathetic tripping of relay R2, because it is not designed or not op designed to operate for the fault which is occurring in the upper line. Now, then we can say about loss of coordination problem. So loss of coordination means, as we have discussed in the previous slides, there will be a time gap between our relay. So this time gap should be maintained. That is called coordination time interval. But if you have different type of photovoltaic sources, like you can having two type of sources may be possible. One will be higher voltage level, higher power capacity, which is connected to the bus, that is called central PV. And if you are having small PV, they are connected to the buses in the distribution system. They are called distributed PV. So there is a possibility that whenever there is a fault in line Z2, then fault current may be contributed from this PV sources. Now let us consider that when we are having a fault in the line without PV, there is a fault current up to 5 PSM up to 5 ampere. So normally they are coordinated. So the time of operation TOPA and TOPB is nothing but the reduction is the time of CTI which is maintained. But if you include the PV, what will happen? The fault current for this B we are considering, the fault current which is nothing but R3 we are having, the R3 which is nothing but blue characteristic, the fault current is increasing, because the fault current will be also contributed from this PV source. Similarly, if you consider this green one, then fault current for this relay R2, that will decrease. Now you observe that the operating point, the time of operation for relay R3, which is shifted to V dash, and the time of operation for relay R2, which is shifted to A dash. So the CTI, which is nothing but earlier A to B, now it has become A dash to B dash. So it has increased. Means because of this PG, we have given a time delay which is increasing to what A dash to B dash. It means that if the relay which is R2 is not operating, then this the relay we are having at R2, it will operate with a time delay. Means we are deliberately delaying the fault clearance, which is not good. And during this period, the because of the fault sustained, the other equipment may blow up. So we have to design the system in such a way that the relay coordination must be maintained. The second one is called, we have several type of transient fault. So because of the transient fault, it may be possible that our system or the relay may operate. So for that reason, we have reclosure. But when we are trying to reclose, what will have, definitely they have to be synchronized on the both the sides. But if you are having renewable at the other end, then synchronization of this synchronous generator and the PV-based generator is a difficult task. So auto reclosing, whenever we are utilizing, then it is very difficult to obtain the auto reclosion of a system wherever we are considering the renewable energy sources are present in our system. So if you talk about the coordination issue we have discussed in the previous slide, why the coordination is lost, and it depends on how much fault current is contributed from the source. So the coordination loss depends on intermittent nature of renewable energy sources, fault current dependency on the distributed generation, fault current limitation in the inverter based DG, changes in the network topology, directional and magnitude changes in the fault current. So how to handle all these issues? Because we cannot avoid the penetration of photovoltaic sources in our distribution system. But if they are coming in our distribution system, then two types of operation may be possible. Either microgrid operation without grid connection or with grid connection. In both the things, the fault current magnitude will change. So we have to address this issue and we have to solve all these issues. Otherwise, it is not possible. Yeah, okay. Yeah, okay. Okay. So let me go to the figure we are having. This is the figure which is simulated. So we have a PV source which is connected to the bus nearby the R3. So earlier, let us consider this PV source is not connected. So fault current is contributed from the synchronous generator. So if the fault current is contributed from the synchronous generator, then first this R3 should operate for a fault in the line Z2. And if the R3 is not operating, with a time delay, this R2 should operate. So that is the point which is crossing the red line, that is the PSM line. So we have identified two points, that is over the red characteristic, we are having point A. Over the blue characteristic, we are having point B. So time of operation A minus time of operation B is nothing but the CTI, which is coordinated. Now, if you include the PV nearby this R3, what will happen? Fault current for this R3 will increase. So if you include this PV, then now the fault current for R3 is increasing. So PSM will increase and time of operation for this R3 will increase up to the point B dash. However, since the control technique of this PV will maintain the voltage at this bus R3, then fault current which is coming from the grid, that will decrease, and it will cross the red characteristic at the point A dash. Now, what is the delay we are having? Now, the relay R3 is operating at B dash and the relay R2 is operating at A dash. So the time of operation or the delay we are having is now A dash to B dash. So that is, we can observe from this figure that coordination time has been increased. Hence the delay of operation of R2 has been increased. Now you consider a case that this, if the R3 is not operating, then the backup will operate, which is nothing but provided by R2, but it is operating with a time delay. So if it is operating the time delay, we are deliberately allowing the fault. हम लोग जानबूझ के fault को allow कर रहे हैं, which is not desired. So that is the maloperation of the system with inclusion of PD in our system. I hope it is clear. Okay. So basically, when we are talking about this inverter-based DG, then there may be possible that we have several transient faults which may occur in our distribution system. So because of this transient fault, there is a chance that the DG may be disconnected. So this disconnection of a DG because of transients in our system, what it will do, it will create a reliability issue. And the switches we are having in the inverter, they does not have that much capacity to handle the higher voltage across them. So we have to design the switches or we have to design the control technique in such a way that these two objectives will be achieved. Means they can withstand the fault current and they will handle the transient type of fault. So what we have done for this case, we have used a low voltage ride through to protect our different switches we are having in our inverter, as well as this inverter based DG, they are allowed to connected in the grid if the voltage level is not decreasing for a particular value. So this integration of DG during fault is suggested, but resynchronization is also a issue. So the method is not recommended in case of highly penetrated distribution system. Otherwise, what you observe, disconnection of the DGs will be continuously there, and we cannot have a continuous supply which is not reliable. With this trend, we may observe that new grid codes suggest that DG remain connected in the grid during fault to support the voltage at buses and improve the reliability. This term is nothing but known as low voltage ride through. So the grid code, if you observe that by the IEEE standard, we may have the low thermal overloading capacity for electronic switches. So for this region, if the voltage is less than 0.5 per unit, will allow the disintegration in 6 cycles. If it is 0.5 to 0.88, then we'll allow the switches to be connected 120 cycles. If it is 0.88 to 1.1 per unit, that is the normal operation. Similarly, for higher voltage also. We may also have the frequency codes, that is the frequency is varying less than 0.59.3, then it will be allowed for 6 cycles. Then if it is less than 60.5, then frequency greater than 60.5, it will be allowed for 5 cycles. And it also depends what type of control technique we are applying for the inverter based DG. So basically, the control technique available, power control, current control, voltage control technique are available. Then we also have dynamic voltage support to maintain the voltage at the different buses. During this period, normal case, what we are having will be supplying only active power, However, during fault, we'll try to maintain the voltage. So the if you observe the blue line, that is the ID, which is decreasing during fault, and the other line, which is nothing but IQ, is increasing during the fault. And maximum current, we have to limit it to 200 because the switches, they are not able to withstand a higher current. So for this region, what you observe, according to our control technique, we have modulated the fault current. So since the fault current is modulated, that will create a problem for our fault detection technique, which rely on the magnitude of fault current that we are considering as a overcurrent relay. So basically, what you may observe that the change in voltage we are having during fault. So the change in voltage is used to input the current or power. So basically, the imaginary part of current is nothing but maintained as I maximum. And if you observe that IM, imaginary factor of IPQ, is nothing but given by imaginary part of IPQLS plus some factor K into DU minus 0.1. So the change in voltage is more, definitely the input power, the reactive power supplied will be also more. So these are the different techniques that we are applying for voltage control. We tap the voltage from the grid side and we convert into DQ, and we also take the frequency. So basically the inverter switching will be controlled in such a that we'll be considering the voltage and the frequency should be maintained. So these are the different control technique and different issues we have considered for our inverter based DG, which are available in our system. That is, we are considering the AC system only. But how they are affecting the our protection technique. As of new, the protection technique we are using in our distribution system, they are based on the current value. Means if you are having the current, they are taking the current as an input and they are deciding either the fault is there or not. By inclusion of the DG, the current magnitude has changed, and the control technique we are having in our distributed generation inverter, then that is also affecting the fault current. So all this technique we are observing, they will affect the decision of a relay in our distribution system with inclusion of distributed generation. So that is a huge problem in our hand. Then how it can be handled, how it can be changed. So probably the problem is occurring because of DG. So we may manage the DG. Means if you disintegrate the DG during fault, then may be possible that fault current will be contributed from the generator. Or we may tell this is the maximum capacity of the DG we should include in our system, so that beyond this one we cannot include our DG because it affects the fault current. Location of the DG, if you locate the DG at the beginning of the distribution system, that is also helpful for us. Managing the fault current by using different type of reactors and fault current limiters, that is also possible. However, all these methods, disintegration of DG, limiting the fault current rating, and locating the DG, they bound us to include the DG at a different location according to the availability or according to our system specification. So these methods are not preferred. Then what is the other method we are having? The other method are changing the system protection scheme. Means if you're talking about the protection scheme, we have differential relay, we have distance relay. So with communication system, the protection technique which are using, that is overcurrent relay or current as a system, then you can change that. We can have a differential protection also. So, but taking using the differential relay, we need communication channel, and with communication channel, the cost of the protection technique is always increasing. But as of you know that for a protection system, we use only 5 to 10% of the total cost. We does not go beyond that. So that is not a correct solution when you are going to put more number of money in the protection system. Then we may have offline setting of this relay, because if you know the network and offline you find out a better technique to or better setting, then that is also good. But our network is continuously changing, so offline setting we have a limitation and that is impractical also. Online setting, that is of relay, that is also a possible system. So, but online setting requires communication also, that will use a huge cost. Then if you observe these two things, managing the DG side and managing the protection system side. So what we are discussing, either we will manage the fault current from the DG side, DG side से हम लोग fault current को manage करने का कोशिश करेंगे, या फिर जिसके लिए प्रोटेक्शन इशू हो रहा है वो प्रोटेक्शन टेक्निक को ही चेंज कर दे, वो प्रोटेक्शन को ही हम लोग चेंज कर दे. But these two things are possible, but we have some issues. We cannot think in such a way that we'll include go for 100% conversion. We cannot think that we'll put that much cost in our protection system. Then the other solution is we'll use the same overcurrent relay or fuses or reclosures, and using this relay, we will try to modify some technique, or we'll try to modify, we'll take some extra features so that the overcurrent relay will operate in a correct way. Uh, we can so that we can go for higher level of penetration. Okay, so these are the things we have discussed. That is management of the DG, disintegration of the DG is the possible way solution, but removal of the DG for the temporary fault or resynchronization issue, reliability is affected. Limiting the DG rating, that is optimization technique, will be also not applicable, not suitable for varying request. Locating the DG means optimization is very difficult for this one. Managing the fault current, optimization difficult for a complex network, and extra cost of the current limiter is also a factor. Modifying the relay setting, already I told discuss that the differential relay may be applicable, but it will increase the cost of the communication system. Online setting of the relay, high competition of the burden will be there on the system, so it cannot be applied at every place of the distribution system. So this is the place where we are having, that is we'll use the overcurrent relay, and we'll design a new technique which will be modifying the overcurrent relay principle. Now, what is the adaptive setting? Then we are considering that setting of this relay is done considering several assumptions. We'll assume that the generator capacity is this, will be assume that the maximum and full load current will be this. So after that, if you observe that different configuration and different things, then we'll consider that this is the maximum load current, this is the minimum fault current. Then we have a setting, so we have a setting after some calculation. However, the setting will not be perfect for several system conditions, because the system condition is changing. So if the system condition changes, then the relay setting is not appropriate. And inclusion of a photovoltaic and a different type of renewables, they provide a changes in our system condition. Like in case of PV, if you consider the irradiance is continuously changing. So the current which is coming from the system, that is PV, that is also changing. So because of such things, the continuous variation will be there in the system condition. So the setting of this relay, which are considering the variation of our source, so that is not fixed. So we have to go for adaptive setting. So what are these advantages we are having? It is first, the selectivity will improve, it is reliable. But disadvantages will be not efficient for larger network configuration, excessive memory and offline analysis data is required. So the challenges are here. We required a faster communication system, high computational speed, huge memory is required, Big data is required for trading, and high initial investment is also required. But will achieve these advantages like the operation will be reliable and selective. So considering this, we have tried a method by which we can solve the issue with a overcurrent relay. Now consider the PV is present at the end of the distribution system to minimize the losses as well as improve the voltage profile. So if the PV is there in the system and the relays are present, they are designed according to the synchronous generator. Now our work is to operate the relay in such a way that the coordination of the relay must be there. So we have the normal operation. Basically, we know that PV always operate in such a way that the sequence current will be equal to zero. So basically, they provide zero sequence current, which is very zero. So if the grid is not connected and the power is coming from the PV, then the fault current which is fed from the PV will not have the zero sequence current. So if this zero sequence current is zero and IAIB IC is less than the I threshold, then it is a balanced network and we can consider there is no fault in our system. Case 2, we can have it is a symmetrical fault, means I naught is equal to 0, but IAIB IC is greater than equal to threshold. Then the fault current contributed from grid. If it is at the maximum value, that is IAIB is equal to 2 per unit, then we can have the fault current contribution from the PV side. Then case 3, we are having that is line to ground fault and double line to ground fault. So in this case, if it is from grid side, then I naught is not equal to I naught is equal to 0. So basically, we have used the characteristic of a PV to detect either the fault is from PV side or it is from the synchronous generator side. If the fault is from the synchronous generator side, then no need to change the setting of this relay. But if the fault is there from the PV side, then we have to change the setting of this relay. So to change the setting of this relay, what we normally do, we compute the fault current at the PV bus if a synchronous generator is connected. So basically, there is a PV is connected at the bus, but if the PV is not connected and the synchronous generator is connected with that capacity, then what will be the fault current? And using that fault current, we have detected the fault in our system. So this is the algorithm. So basically, we are having directional overcurrent relay that is per phase, and I naught is measured. If I naught is less than threshold, then we are considering it is uh, uh, grid. If it is less than the threshold value, then it is the PV side, or if it is greater than that, then it is the grid side. So according to that, finally we are computing the fault current from a PV side relay. The second technique we have used, that is called estimated voltage based gain. Means in the first case we have estimated the current, and in the second case we have estimated the voltage. Means we have included the voltage in our system in the methodology. As you observe that the earlier case we are having TOP is 0.14 into TMS divided by PSM to the power 0.02 minus 1. However, in case of this fault, definitely this voltage will be affected. So we have created the fault at a different bus in the previous diagram. We have seen that the voltage is also getting affected. This voltage is decreasing. We have also considered the control technique which is available in the inverter based DC. So we have taken this the additional factor, that is e to the power 1 upon 1 minus vf to the power k. And for different values of k, we have chosen, that is k is equal to 2, k is equal to 1, k is equal to 0. We have seen that the time of operation. So if we include the with values of k for different values, then automatically the time of operation is decreasing. So that we required. So including the fault voltage, which is measured at the relay bus. So we can have a better algorithm. So what we have done, first we have taken the SCADA data. So is the network is islanded? Yes. If it is islanded, then we have to go for the next estimation process, estimation of the fault voltage VF without DC, and obtain the branch current injected due to DC with LVRT, obtain the time of operation of the relays with a modified setting. If it is no, then is the DG is connected along with the external grid? Yes. Then again you have to go for this calculation. If it is no, then k is equal to 0. Then means the TOP will be, that is the conventional setting. So these are the results we are having for this above case. That fault is there in the buses 4 and 5, and the case 2 is the fault is there in the 7 and 8. So earlier case, if you observe the CTI in CTI 1, that is 1.202, which is much more than the changes that CTI we required. So normally we required 0.2 to 0.4. So after that, the CTI has been increased to the modified setting. So if you observe, the changes in our CTI is very high, that is 63% and 64, 67%. Still, we are unable to achieve this CTI in between 0.2 to 0.4, which is desirable. So still the problem is there, and further work may be done with this one. So basically, these are the control technique applicable. You can see the active power, reactive power flow, P and Q, during the PV current and the power injection. So during the dynamic voltage control mode, the imaginary part of I is increasing to 2 per minute, and during this point, the reactive power is supplied and active power is not there. So if you observe the voltage, that is within no DC, the voltage was 0. However, the voltage profile for the different buses is increasing. At bus 3, the voltage occurs, that is 0, and bus 12 up to that one, the voltage is continuously increasing, but it is less than 0.2. So with this, we can say that the voltage and current, if you use the voltage, then we can have a better protection technique, which will be applicable for our system. Now, the another technique we have used, that is called inverse cosine relay. Now, in this case, we have used the control technique of inverter, which normally take the power factor. Normally, it operates as a unity power factor. However, in case of our distribution system, the synchronous generator, the power factor will be less than that, because we'll be having the reactive nature of the system. And if the power factor, if you observe, if it is less than 0.85, definitely some issues will be there. So there is a possibility that the synchronous generator is not connected, and the fault current is supplied from the PVC, that is photovoltaic sources. So we are adding a factor that is called correction factor. So correction factor is nothing but cos of alpha divided by cos of beta inverse, where cos alpha cosine of the fault current and cosine beta the threshold is given as 0.8. As per the IEGC, the power factor, worst power factor is 0.9. So we are considering that TOP will be nothing but equal to TSM into 0.14. So earlier we are taking that factor is PSM. Now that PSM is modified with PSM to CF square. Why square? Because we have tried with CF1, CF2, CF So we have find out that we are getting better result with CF square. So this correction factor is when it is multiplied, then we have seen that the performance of this relay, the time of operation of this relay is increasing. So with a little modification that is possible, that will identify the relay operation is has been improved. So in this table, you can see that fault current for R1. So according to the fault current R1, the uh, overcurrent relay is unable to detect the fault. But with this inverse cosine relay, now we can have a detection of the fault. The fault current is now we can detect the fault. This is the benefit we have used by using a inverse cosine relay. So these are the hardware results we have from a real-time system. So in the real time also we have tested this method, and we have seen that the relay performance has been improved. Now in this case, that is this is another technique which we are telling it is a quadrature based overcurrent relay. As IQ component of the PV unit is going to modulate the support of voltage during fault. Hence, Q-axis component is used here to propose the quadrature basis overcurrent relay. So we are taking IP is equal to means some factor k into gamma into ID rated. So alpha is equal to IQ into I alpha. So k is nothing but tan inverse of power factor of the threshold. So finally, our TOP will be TSM into 0.14 divided by alpha to the power 0.02 minus 1. So it has been observed that when alpha is greater than 1, then fault has occurred. When alpha is less than 1, the fault has not occurred. So this is the system we have considered, that the PB is present at the end of the system, and it has been observed that when we are considering the fault, then the TOP of the system is TOP of the relay is decreasing, and we are having a better performance. So in this one, we have also solved the sympathetic tripping by observing the power factor of the system. So these are nothing but the better technique we can solve the relay blinding as well as the sympathetic tripping. Now, we have also used the adaptive fault detection technique to prevent the relay blinding. So we have considered a DG at the bus number 14, and inclusion of DG at bus number 14, we have observed that maloperation of overcurrent relay due to this DG infect. So this concept tells us that normally if you go for a signal, the current signal will be sinusoidal, and if it is not sinusoidal, then you can have the fundamental frequency by using different filtering technique. So by using a low pass filter, if this is the signal we are having, then what we can do, we can see there is a increase in current during the fault. In normal case, if you consider the samples of current at the red mark, red pointer, summation of these two things, it will be having very less value, or it is nearly equal to 0. However, whenever there is a fault, then what will happen? There is an increase in current, or there is an increase in this value. So then we have defined some threshold. So how to decide the threshold? We have taken three indices, that is rho A, rho B, rho C for phase A, B, C. That is equal to I of t plus I of t plus t by 2. So normally this rho A, rho B, rho C cannot be helpful for detection of a symmetrical fault. So we have taken another value, that is E1 is equal to rho A minus rho B, and E2 is equal to rho B minus rho C, and E3 is equal to rho C minus rho A. So even if there is a symmetrical fault during this period, sometimes may be possible that fault current will be similar, so it cannot be detected. To obtain a threshold, we have simulated at least 3000 data sets. So considering the fault data, which is the red one, and considering the load data, which is the blue one, we have selected a threshold. So the threshold is selected at 45 ampere, and to obtain the decision for a three-phase fault, what we have taken we have taken the decaying DC, because during three-phase fault, normally this decaying DC will be present in our system. So considering the different fault resistance and the load conditions, we have simulated, and we have find out that DC decaying DC component will be helpful for providing the either it is the change is there due to load, or the change is there due to fault. So considering all the things, we have this algorithm. So we will take the current sample, extraction of the fundamental signal by using FFT algorithm. Then we are taking the indices by using 2, 3, 4. Then calculation of E1, E2, E3 using 5, 6, 7 equation. So we are considering E1, E2, E3 is greater than threshold. If it is S, then fault. Now we require the support of this decaying DC. If it is there, then it is unable to decide that if it is not equal to greater than equal to threshold, then we will consider decaying DC. If this decaying DC is having some value that is greater than equal to K naught, then if it is yes, then there is a fault, or if it is no, then there is no fault situation. So we have considered the line to ground fault as well as symmetrical fault. So there is a load change which is simulated in the first case. As you observe that the magnitude of phase A, phase B is presented here in the red color, and in the third figure, E1, E2, E3 is presented. So where it is less than the threshold value. So decaying DC also shows that the blue one, which is less than the threshold value. So for DG penetration, the fault is not detected because DG penetration has increased the current level. However, if you observe the LG fault, then this E1, E2, E3 value is very higher compared to the threshold value. So the fault is detected. Now, apart from this present technique, what we are considering to modify the overcurrent relay characteristic, now there is a option we are having that will go for other different type of relay. That is distance relay, differential relay, frequency-based transformation of relay, AI-based technique, and multi-agent based technique. Now, what will be the problem with the distance relay? Why we cannot apply the distance relay in our distribution system? So there will be a problem that is called, if we are having a high penetration level, then under its effect due to infeed, that is the most problem we can see. Power swing, because we'll be having multiple sources, then considering that power swing will be also available. Malapparition due to source impedance, changes in source impedance because of different control technique we apply in terms of our inverter, that is will be there. Then malapparition due to current limitation whenever we are talking about differential relay. Yeah, and differential relay is also having another fact that when you consider the uh, communication system, it will increase the cost of the protection system. So the current limitation which is occurring in our system because of our different type of control technique, that causes a problem in our system, because the phasers what we have from the synchronous generator, earlier they are something different, and now the control technique modulates the phasor in our system. So the phasor-based technique or the phasor-based analysis for the fault what we are having, that is not effective, or that is not applicable now. So we engineers, we electrical engineers who are working in a power system, they have a big task in our hand. So by which we'll be going for a new technique to design the new protection technique and other things. Now these are the issues we have understood with the AC system. But we have also seen that in our distribution system, possibly we'll think that why not DC? Why will convert the DC to AC, and we can have a conversion loss also, that will also reduce our efficiency. So there is a possibility that we'll try to produce the power to DC, or DC to DC conversion will be there, as well as we'll supply the power to the DC loads. But it has also some means protection issues. What will be that? So we may have non-availability of a current zero. In case of our AC system, the benefit is that whenever you are trying to break it, we have to break it at a current zero. If you are breaking it at a current zero, then our system will be safe. We can break it very easily. So why the DC braking is difficult? That is only because that a magnitude of DC current whenever it is very high, our the circuit breakers are not designed uh, to design the uh, to break the circuit at a higher current level, and current zero is also not available. Fault detection standards are also not defined. Whatever the fault detection standards are there, issues with the grounding issues were also there. Sources of arc fault, variation of storage energy, then changes in our temperature, broken cables, then degradation of the solder joints, flexible cable insulation in junction boxes, corrosion of the conductor. These all are the issues we are having in DC protection system. Then what are the solutions we are having? So basically, to break the circuit, we have fuses. Some of them are conventional fuses, or some of them are semiconductor, DC breakers, that is molded case, vacuum CD, hybrid solid vacuum circuit breaker, protective relay like DC power relays, digital relay. Then we have arc fault interrupter like arc circuit breaker, AFI, combination of arc fault circuit interrupter, solid state circuit breaker. Normally we use the uh, solid state switches to generate the current zero. Then after that we break that. So we have gate turn off thyristor, then emitter turn off thyristor, insulator gate bipolar transistor, insulator gate communicator thyristor, coupled inductor, and hybrid circuit breaker in combination of DCCD and SSCD. So these are the possible options we are having when you are thinking about the system. So, as of you observed in our previous discussion, that the distribution system the uh, without the renewables, it is not possible. And so we have to plan our distribution system in such a way that we have to go for new techniques to detect the fault. So OCR uh, it is sufficient to protect AC microgrid. However, OCR is not sufficient to protect the grid with renewable. So this OCR may be requires inclusion of a distance and a differential scheme, but it will increase the cost of the system as well as coordination and dependability of the relay is to be tested for all combinations. All the relay may be tested for practical conditions. So what are the future scope we are having means with inverter based DG? Testing of a distance relay for a microgrid, testing of a differential relay for microgrid, AI based technique for microgrid for wide range of variation, achieving the resiliency of the grid by using AI. So these are the key references I am having. I am eagerable to take some questions from the audience if you are having.
I request all the participants. Please, ma'am, take one. Okay.
Dear participants, we are open for question and answer session. If you have any questions from our expert speaker, you may ask now.
Sir, I have one question, sir. Sir,
Yeah.
sir, we are the main problem in here. The protection issue is the fault current shared by these DGs.
Yeah, yeah.
Okay, sir. Then if we are connecting these DGs in our system, and we know that how much is the rating of those system, how much fault current they are going to share, then why not we can make these relays digitally we can change the time setting or current setting of these relays in real time.
That is possible. That's why we have given the option that it will, if you observe I'm going to the slide, we have given what are the options we are having. So basically, so here if you observe the third one, online setting of the relay. But online setting of this relay requires a high computation, means it will be very difficult for complex network and communication system is required. But if the communication system fails, normally the communication system fails in our day-to-day life. If the communication system fails, then online setting is also not possible. So the proposition is in such a way that that is possible, but to have a complex network, then high computational burden is over the system, as well as the communication system should be perfect. If the communication system is not there, then changing the setting according to the system condition changes. As you are telling, you know how much current will be coming from the DG, and according to that you can change the setting. That is not applicable. So for that reason, we are trying to modify from the relay side that the relay algorithm may be modified so that the malapration may be prevented.
Uh, Thank you, sir. Sir, related to that, this might look absurd, but can we use satellite communication for these things?
Satellite communication may be possible for monitoring, but when you talk about a relay takes a decision in a very fast time. Means within 2 to 3 cycles, we have to take a decision so that fault may be clear. We cannot allow the fault for a longer period, like 1 second, 2 seconds. That is not possible. So satellite communication itself, when we send the data to satellite and from the satellite to come the data, then it takes huge time. Means maybe 10 seconds, that much time is required for the total signal receiving and signal sending. So the satellite communication is not a feasible option we are having for the total system. Only one way, if you have fiber optics at all the point of the city, like as of you know that fiber optics are available in every point of our city, and wherever these metros are there, these metros will be supplied from distributed generation, solar, wind, and other things. So that fiber optic may be a possible communication channel by which you can share the signal and you can allow it for protection. But problem is that when communication channel fails, then what to do? If your algorithm depends on communication channel, then communication channel fails, you are totally blind. You cannot take a decision. So for that reason, adaptive setting, what we are taking, modifying the fault current sense by the relay, or we can have a changes in our setting of this relay, that is preferred.
Okay, sir. Thank you, sir. Thank you so much, sir.
Thank you so much, sir. Do we have any other questions? Do we have any other questions from the participants?
Okay, if there is no question, I will ask the audience that this protection is a very difficult part for the distribution system and achieving the coordination in our distribution system using overcurrent relay. Then it is a very difficult task now at our hand. So, so many people work in that stability aspect, power quality aspect, but very less people work in that protection aspect. So, but we need a complete solution whenever we are thinking about the distributed generation in our distribution system. Definitely, protection issues will be there. And if you students as well as the faculties would be working in this area, then definitely we are there to help you. And the problem in this side is that the system data as well as the system condition is not defined. So we have to assume so many things for the setting of this relay. So that is a difficult task for us. When we set and we take so many assumptions, then it is very difficult to convince somebody. As if you are checking the control as well as power quality aspect, the system is defined. The system, because work is continuously going on in that area from last 10 to 15 years. So there are challenges, but there are options also that it will work. So I will encourage people they should work in this area, and we are open that if you have some idea and you need some support to do the simulation in MATLAB, to do the simulation in other software, PSCAD, Excellent, then we can help you, and we can collaborate also in different domain. Yeah, thank you all.
Sir, could you please share your email ID in the chat box so that all the participants could have it and they can share contents or share the knowledge?
Yeah, yeah. I will share my slides also. That will be helpful for our participants.
Hmm.
Uh, I'm just sharing my email ID.
Okay, sir.
Okay, sir. Thank you, sir. Thank you for taking out time from this for this online FDP and providing us great knowledge about the topic. We'll surely reconnect with you for future events.
Yeah, thank you, ma'am.
Thank you, sir. Thank you so much, sir. Thank you.
Thank you so much, sir.
Thank you.
I have completed little early, I think. I thought more questions will be having.
No, sir, it was great, sir. It was a
No,
really
sir, it was a great
pleasure,
session.
sir.
Okay, I will share my slides with Dr. Kishore, and
Yes,
he
sir.
will share with our participants.
Okay, sir.
Sir, we have also
Okay,
recorded.
thank you. Thank
We have also recorded your session. So could we means publish this on our department's channel, YouTube channel?
No, no issue. Knowledge should be distributed. Knowledge, it is there. We have this knowledge from our seniors. We have this knowledge from our community.
Yes,
So
sir.
we cannot stop this knowledge to flow.
Okay, sir.
Let this knowledge to flow, and we'll have more students to come up for this protection work.
Thank you, sir. It's a great thought. Thank you so much.
Thank you, sir.